Good morning, everyone. As the chairman says, my name is Mario Álvarez, and I work for Ikerlan, which is a research and development center located at the Basque Country. My presentation is divided in 4 different topics. First, the introduction. Then I will proceed with a framework. Then I will show my results, and I will conclude with conclusions. Well, as introduction, I would like to remark that in the wind energy industry, a very important and relevant sector is the offshore wind turbines. That's the reason that we chose as case study an offshore monopile foundation, which is commonly made with S355 steel. These monopile foundations are subjected to corrosion, especially in the splash zone when alternating wet and dry stages occurs, and also to the combined action with mechanical loads. This simultaneous action of both corrosion and mechanical loads leads to the corrosion fatigue phenomena. This corrosion fatigue is responsible for external and internal corrosion issues, significant pitting corrosion rate increment under wet and dry conditions, structural loads leading to dynamic stresses that increase corrosion pit growth kinetics. And considering all these previously mentioned factors, we decided to consider the fatigue-loving corrosion in the corrosive environment modeled phenomenologically as a degradation of material fatigue properties. Taking into account the importance of this corrosion fatigue phenomena in the offshore monopile foundations as a failure mechanism, the motivation of this work is to gather information to be used towards decision-making in predictive O&M and the revision of designing rules in offshore monopiles with localized corrosion defects. In order to achieve this goal, we defined several objectives as to study the effect of wet and dry conditions during a combined corrosion fatigue process by means of a phenomenological approach to establish a comparison between experimental results and corrosion fatigue SN curves constructed with theoretical models published in the literature. And finally, to compare experimental results and analytical predictions with conservative design curves for free corrosion in seawater. The framework in this study consisted in 3 different stages. The first one is what considered the experimental testing in order to characterize the mechanical properties of the material, the pit size, and to obtain an experimental corrosion fatigue SN curve. The second stage consisted in the selection of a SN curve in air from literature. And the third stage was the application of analytical models in order to characterize or construct SN curves in corrosive environment. It is important to remark that the mechanical properties and the pit size obtained in the first stage and the SN curve in air from literature were used as input parameters in the analytical models. And the experimental corrosion fatigue curve was used to validate the predictions obtained from these analytical models. The samples in this study were manufactured from steel S355G10+M with mechanical properties shown in the image. And in the fatigue samples, we generated a corrosion pit in the center of the sample using a ferric chloride solution. This corrosion pit was considered as a semi-elliptical defect with a pit size in the range of 126 to 200 microns deep. Fatigue testing was performed using in situ corrosion fatigue testing, considering 2 different wetting conditions. The first one considered a wet and dry stage in order to represent more or less the corrosion present in the splash zone. So in this case, we use the recommendations stated in the ISO standard, using a period of 10 minutes of wetting and 15 minutes of dry stage. In the second conditions, we try to represent the immersion zone. So in this case, the fatigue testing was performed using a continuous flow of artificial seawater all the time. In the fatigue test, the load ratio was 0.1 with a frequency of 1 Hertz, using artificial seawater with a salt content of 3.5%, a flow rate of 100 milliliters per minute. And all this, the test rig was constructed using a plexiglass container. Now I will show the experimental results. In this image, you can observe the progression of corrosion when the samples were tested in a wet-dry cycling. In the next image, you can see the aspect of corrosion when using a wet condition. It is important to point out that after failure, in all cases, we checked that the crack initiation was produced in the artificial generated pit, as you can see in the image. Now, prior to present the results comparison, I would like to say that we define an expected range for corrosion fatigue results using upper and lower bounds. The upper bound consisted of the SN curve in air, and the lower bound was defined by the SN design curves proposed by the codes DMB and British Standard. In the image, I'm showing the fatigue life experimental results obtained during the wetting condition and the wet and dry condition. In this image, we can observe a fatigue life reduction when compared to the SN curve in air. And also, this degradation was more severe when testing in the wet-dry cycle. This degradation was estimated in the case of the wet condition around 34 to 69% and 61 to 74% for the wet and dry condition. In the next slide, I will present the SN curves constructed by means of 3 different analytical models. In the first case, we selected an analytical model proposed in the publication of Kenji, and this method was based in the construction of SN curves through the input parameters obtained from pitting characterization and roughness. In this case, this model is these 2 lines, and we can observe that non-conservative predictions were obtained above 300,000 cycles. In the next case, we employed the method proposed by Aldazorilla. In this method, the author manipulates the slope of the SN curve using a modified Baskin's law. In this case, the prediction obtained produce conservative predictions above 50,000 cycles. And finally, the last analytical method that we consider in this research was the method proposed by Vergara. This is a similar method that compared to the previous one, that uses a linear increase of the difference between non-corrosive and corrosive fatigue strength. In this case, in this prediction, the conservative predictions were below 10 million cycles. Now I will conclude my presentation with the conclusions, and we can say that life reduction was observed when corrosion fatigue testing was performed in artificial seawater environment. The application of wet and dry cycling during corrosion fatigue tests led to higher degrees in fatigue life. These results suggest a more severe corrosion during wet and dry cycling. Both analytical methods based in SN curve slope manipulation led to less conservative estimation than design curves proposed by codes DMB and British Standard. However, the method published by Vergara provided even less conservative estimations than Adazorilla in the range of 300,000 to 10 million cycles. Although SN curves constructed with phenomenological models cannot be used for the same purposes due to the reduced number of experimental points, they can provide an acceptable estimate of the SN fatigue behavior of the corroded material. And finally, these fatigue life estimations can be very useful in the inspection and repair activities with observed conservatism between experimental data and design curves provided by the codes. Okay. Thank you. Thank you very much.